Hello everybody, we start our lecture. So section 12.1, volumes of solids of revolution. This section, like other applications, other geometric applications of definite integrals, is not so rigorous as other parts of our course. Why? Because of our course is univariate calculus, right? And surfaces of solids of revolution, that is a three-dimensional object, right? But I don't want to go deeply inside multivariate things now. So we will proceed in a different way, namely we'll start from univariate thing. So as usually we have a non-negative function on an interval y equals to f of x. F of x is non-negative. And we try to understand how one can compute volume for the solid which is obtained by rotation. So let us rotate. We rotate our trapezoidal figure. We rotate it around x-axis, like that. So we rotate and we try to understand how to compute the volume of such. Okay, let me draw it in a more solid way. Okay. That is our solid of revolution. We rotate the graph around x-axis and we obtain a solid, and we want to compute the volume of that solid. So once again, I don't want to go deeply inside to the question, what is volume? Now, we'll consider it in more details during next semester. There will be multi-variable calculus course, and we'll consider in more details that question. But I will refer to a fact from school geometry, elementary geometry, that is about volume of cylinder. So what is volume of cylinder? So if we have a cylinder of height h and radius of the base is r, then volume is pi r squared h. So that is the fact which I'll use now. So I don't know what is volume, but I know the formula. That is how we'll proceed now. Okay, then, once we know volume of cylinder, how we can compute the volume of such a solid of revolution? So, we know nothing else this fact about volumes. So, what we can do? If we'll consider like before some partition of our j minus 1 xj, so we consider a partition right? There is a partition of our interval, and as usually we take infimum over one interval okay, j, let's say j minus 1 xj, yeah. So that is what I draw. That is, the height is infimum here. And then what we'll do, if we rotate, instead of our graph, if we'll rotate this straight line, then what we'll obtain? Then we'll obtain a small cylinder, right? Small cylinder, thin, better to say, right? Thin cylinder. A thin cylinder. And what is volume of this thin cylinder? The volume of this thin cylinder, Vj, let's say, is equal to what? So, what is the radius of the base? So, you see, the cylinder lies horizontally, not vertically like here, but it lies horizontally. The height here, right? Height is delta xj, right? This distance between xj minus 1 and xj, the height of this thin cylinder. And what is radius of the base? Radius of the base for this cylinder is equal to infimum. So mj. So it means that volume of this thin cylinder is equal to mj times delta xj, right? Then what we'll do? We computed volume of this thin cylinder, then we'll consider all such cylinders which correspond to other intervals, right? So we take many such cylinders. I don't want to draw extra lines because it will be not clear. So we make many such thin cylinders, right? And then add volumes of all of them, right? Then we'll obtain some figure, some solid which consists of several thin cylinders, right? And the total volume of this, let's say, V underlined, total volume is equal to sum of those volumes, right? Mj delta xj. So you see what we have. Oh, sorry. I wrote radius is mj, but of course volume is pi mj squared, right? So pi mj squared. Sorry. Okay. Yeah. Radius is mj, but volume is pi r squared h, so pi mj squared delta xj, right? Sorry. So, once again, what I wrote here is volume of a solid which is inside our solid of revolution, right? Analogously, if we consider capital Mj, which is supremum, x in xj minus 1 xj, then, so it means instead of this cylinder which is inside our solid, we'll consider a cylinder which will contain our part, right? So maybe I'll draw the picture somewhere else, so like that, right? So that is an example of such a solid. So you see, again, thin cylinder, right? Thin cylinder. But now this cylinder contains our solid inside itself, right? This thin cylinder contains part of our solid inside. And if we add all those cylinders together, right, then we obtain a figure which contains our solid inside. So, the volume of this greater solid will be equal to pi sum j from 1 up to n capital Mj squared delta xj, right? Then, I don't know what is it, I mean volume of our solid, but obviously from geometrical point of view, obviously, right, that volume of our figure which I want to find is in between. So V bar and capital, V underlined and V overlined. So the volume of our solid of revolution, which I want to find, right, is somewhere between those two volumes. One of them is a volume of a figure which consists of several thin cylinders, and each of those cylinders lie inside our solid. Another volume, V overlined, is the volume of a figure which consists of several thin cylinders, right? But now those cylinders together contain our solid inside, right? So our solid of revolution is between them, right? Somewhere between, roughly speaking. I mean, not the solid, but the volume of this solid is somewhere between the volume, right? So, but look, what is it? That is precisely Leonidovich sum for the function pi f squared. And that is Leonidovich sum for the same function. So if the function f squared is integrable, right, then for sure, what can we say? Those lower and upper Darboux sum then can be made closer and closer to each other, right? And which number is always between them? Only integral. So what we obtain? We obtain the formula, and once again I don't want to use words theorem because I didn't give definition for what is volume yet. But the formula to compute the volume of the solid of revolution, which is obtained by rotating of or maybe of let's say capital phi, where phi phi is given by v equals 2 pi integral from a to b f squared of x dx. Okay, here phi is bounded by x equals to a, x equals to b, y equals to 0, y equals to f of x. And in fact, you see, it is not necessarily non-negative, right? Because if it is negative somewhere because of rotating, it doesn't matter, right? We rotate and we obtain. Shouldn't the second cylinder be the biggest cylinder that we can have? The second cylinder, the biggest cylinder that we can have. What means the biggest cylinder that we can have? Yeah, it is not the biggest, but this cylinder, second cylinder, right, is bigger than our, I mean, not one cylinder, but all those thin cylinders together, right? They are bigger together than our solid. It's true, but what is the biggest? Definitely we can make essentially larger cylinders, right? Like that. Absolutely crazy cylinders, which are definitely bigger. So the biggest is wrong. What is capital phi? No. Rotation of phi, capital phi, here phi is bounded by, that is this figure, which I rotate. That is figure phi. A, B, yeah, that is phi, figure phi. That is figure phi. The biggest cylinder will be in the end the biggest cylinder will be in the end of revolution because it has the maximum f of x. Still, I don't understand. I'm talking about the same, that we have a cylinder, I mean, the overlined is a volume of a cylinder which is bigger, not a cylinder, but a figure which consists of several cylinders, which is bigger than our solid of revolution. I don't want to use the words biggest, because that's wrong for this case. Definitely we can find bigger cylinders, but we are not interested in them. Okay. So you see that practically we proved that formula, but we proved without definition, right? We refer to some geometrical intuition which lies behind the notion of volume, one thing. Other thing, we refer to the formula for the volume of cylinder. Once again, this formula was not proved in school, I'm sure, because it used just f squared, because here mj squared, r squared, that is why. F squared, because of this square here. Okay. Now, another story is if we'll try to rotate the same figure about y-axis, right? So what we'll obtain? Yeah, something like that. Something like that. Okay. Yeah. Yeah. So, if we'll rotate our figure phi, yeah, about y-axis, we have another solid of revolution, right? Then how we'll proceed in this case? In this case, we can use shell. Which shell? Okay, let me draw a picture. So the shell is like that. So we have a rectangle and we rotate it. Right, like that. Yeah, and we rotate it about y-axis. That is the shell. So, then what is volume of this shell? Okay. We have three parameters, right? So, the shell is the volume of the shell is computed by the formula 2 pi times, okay, which notation to use? 2 pi times the, that is delta xj for us, right? Then radius, okay, let it be xj minus 1 times xj minus 1, times height, and height is, okay, height is, let it be h. That is volume of this shell. Volume of the shell. And then this is not so easy as before. I mean, you see, because of that parameter, in fact, I wrote here xj minus 1. In fact, it should be the middle, but approximately, right? Let it be like that. That is the middle point of the shell. And the total volume. So if we use those shells, look, so what it means, if I want to compute the volume of our, what I wrote here, that is wrong. So I rotate, that is not necessary, yeah. Oh, no, of course, I forget about this. It was correct, yeah, like that. Yeah, so we rotate our graph about y-axis. So now we try to approximate our volume by adding volumes that curve in that cylinder. No. I don't put that curve in that cylinder. I rotate that curve about y-axis. So we have this curve, right? Our graph of our function. And we rotate the curve about y-axis. Right? Then we obtain this solid of revolution again, right? But it is formed in another way. In fact, you can compute by that formula, but instead of x, you should write y, right? And also, yeah, but this is suitable when you have, yeah, so if you rotate a graph of a function x equals to f of y. Imagine you express x as a function of y, and then you can consider it in a similar manner, right? So change variables y and x, simply. If you are able to do it, I mean change variables, then of course you can compute the volume of the solid of revolution by the same formula as was before. But if it is difficult, then you cannot do it. So how to proceed? To use shells. And then look, so we split our solid of revolution, into the sum of such thin shells, right? Many such shells like that. So you see, as usually, we consider our interval of partition, right? Thin rectangle, and then we proceed with this thin rectangle like here for this shell, right? And then if we sum up all those volumes of shells, right? Sum up all of them, then what we obtain? That is an integral sum, because what is sum of volumes? Sum 2 pi delta xj minus 1 star, and what is h? Okay, h is a value of our function at a point, right? Value of our function at a point. Let's say, doesn't matter, let it be the same. Let it be the same point. And then what is it? That is integral sum of which integral? When diameter of partition, same partition as before, the same partition. As norm of that partition tends to 0, this integral sum tends to 2 pi integral from a to b x f of x dx. Of course, it's true for positive f, for non-negative f of x. So that is formula rotating of phi. I forget to write here rotating of phi about x-axis, right? That is important here. So we rotate about x-axis. And if we rotate about y-axis, that is rotate phi about y-axis. Y-axis. Of course, I'm not sure if you considered volumes of shells in high school. That's another story. So, and now, no questions about volumes, because now I want to go to even more complicated from geometric point of view thing, namely area of surfaces. So now (12.2) area of surface. Of solids of revolution. Why is it not tall cylinders with small radius again? We have rectangle, right? Rectangle. And we rotate this rectangle like that. So this is not a cylinder. That is the difference of two cylinders, shell. Okay. Yeah, in fact, volume of shell precisely, how we may compute. Oh, by the way, about maybe. Okay, I don't want to spend time for that formula because it is used, of course, I mean, volume of a surface of revolution about y-axis, but not so often. Okay. So, surface, area of surface. That is in fact, essentially more complicated thing in general. So, let me recall how we defined length. So, length. I gave you definition. So, length was defined as supremum for lengths of polygonal curves inscribed into our curve. So we took polygonal curves inscribed into our curve and took supremum of all their length. That is the definition of the length. Now we have a surface. I don't want to go deeply inside the definition of what is surface again. Again, there is an intuition, right? Then, in analogy with length, what you can expect? Take many points on our surface, right? And consider polyhedral surfaces inscribed, right? If you proceed in an analogy and take polyhedral surfaces inscribed, right? And it seems very good definition, right? Add all of them and consider supremum of areas of all such polyhedral surfaces. This definition seems to be very natural, right? It's direct generalization of one-dimensional definition, and in fact was used as a definition in several analysis courses in 19th century, while Schwarz found an example. So he constructed what is called Schwarz lantern or Schwarz boot. So what is it? Consider cylinder, very simple surface, extremely simple surface. Cylinder. Usual cylinder, right? Usual cylinder. Let it be of height 1. Height 1. Now, let us divide this cylinder into, height is divided into an equidistant slices, equidistant points, let's say, right? So, like that, right? Equidistant. So we have, let me draw small slice, one slice. It is one slice. And okay, we will proceed further after break. Okay, so we continue. So what we did, cylinder is cut into n equal slices. Okay. Now let's consider one slice and what we'll do with each slice. Split each circumference in our slices into m equal arcs. But what is important? So equal arcs. For two neighboring neighbors, circumferences, circumferences. Points of splitting lie over middle of another small arc. Lies over the middle. So, what it means? We have two neighbors, right? One circumference, another circumference. Two neighbors, right? So we split each of circumferences into m equal arcs. But now, what we should do? Each point is over the middle neighbor. So you see, like that. So you rotate a little bit, right? Just you rotate one circumference with respect to other to make the correspondence like that, right? So every point is precisely of upper circumference, is precisely over the middle of an arc of lower circumference. And we do it for each slice. And now consider triangles inscribed into those points. So, the Schwarz, not sure if I write correctly. The Schwarz lantern consists of all triangles of course not all triangles with vertices in splitting points. So you see, what I draw here is precisely the picture which we'll obtain. And now imagine you have many such slices, and then, okay, it is either lantern, like paper lantern, right? Or boot. But for boot it's a little bit strange. So both names are used. I would say in Russian more often is used that one. But in English seems more often Schwarz lantern, not Schwarz boot. Now, let's try to compute the area. So, how we'll do it? Let me draw a picture. So, what we have, yeah, you see, I draw just one triangle. Let it be A, B, C, right? Yeah. That is one triangle. I want to compute the area of one triangle. You have many such triangles, right? But area of each of those triangles, areas of each of those triangles are equal to each other, right? Because everything is equal to each other. So we have just two parameters, n and n. We split height into n pieces and every circumference into n pieces. Okay, let's compute the area as triangle ABC. Okay, let me, height is 1 as also radius is 1 as well. Radius is 1 as well, to make it easier, right? So, the length, okay, like that, AB, right? Arc AB. What is about arc AB? So, the total length of the circumference is 2 pi length. 2 pi, just 2 pi, right? 2 pi, radius is 1. Over, we split into m pieces, right? So, over m. 2 pi over m. So, if I denote here O as a center of this circumference, right? So, it means this angle is 2 pi over m, right? 2 pi over m. So then, what is length AB? Length AB what is it? So angle is pi over m, right? So OB is 1, hence here we have 2 times sine pi over m, right? That is AB. Okay, maybe I need also to consider, let it be D, and that is M. So we need to compute also MC, right? So MC, length of MC, is equal to square root by Pythagoras theorem of CD squared plus MD squared, right? Okay, what is CD? Let me recall. I divide the height into n equidistant points, so the height of one slice is 1 over n. 1 over n squared, that is CD. What is MD? Oh, okay, let me compute it. MD is 1 minus OM, right? And OM is from the same triangle, 1 minus cosine pi over m. So that is MD, 1 minus cosine pi over m squared. That is MC, right? So the area of one such a triangle is equal to what? 1/2 AB times MC, and that is sine pi over m times square root of 1 over n squared plus 1 minus cosine pi over m squared. That is area of one triangle, right? So what is total area of the surface of that Schwarz lantern? How many triangles we have? In one slice, how many? If we split into m equal arcs, right? So m triangle like that, and m triangle like that, right? Like that and like that. M triangle of each type. So 2 m triangles in one slice. Altogether we have n slices. So total area of surface of Schwarz lantern is 2mn times sine pi over m times square root 1 over n squared plus too much. Okay. I think I can erase it. Is 2mn times sine pi over m times square root of 1 over n squared plus 1 minus cosine pi over m squared, right? Okay, Now let me look at this expression. So what is it? That is 2m sine pi over m times square root of, so I put n into square root, 1 plus n squared times 1 minus cosine pi over m squared. So you see now, we have two parameters. Each of them can be made as large as we want, right? And we can increase both of them independently of each other, right? So how we want. Now let's try to understand what happens. What happens as mn tends to infinity? With this it's easy, right? Because sine pi over m is equivalent to pi over m as m tends to infinity, right? By the first remarkable limit. Sine is equivalent to its argument. So it means this multiplier tends to a finite number, namely 2 pi. So that is, in fact, 2 pi is precisely area of our cylinder, right? As we know. But now what happens with that one? Look, 1 minus cosine pi over m, as we know, we may compute it by Taylor formula, right? And it gives 1 minus pi squared over 2m squared plus O small of 1 over m cubed, and that is pi squared over 2m squared plus little o of 1 over m cubed as m tends to infinity. Now what we have under square root? So look, n squared times 1 minus cosine pi over m squared equals to n squared times pi squared over 2m squared plus little o of 1 over m cubed squared. Look, both n and m tends to infinity independently of each other. It means we can obtain here every number as we want, right? In fact, for example, what we can take? Let's take m equals to m cubed. Then what happens? Both n and m tends to infinity, right? But what happens with this expression? Here we have m power 4, right? And that is m power 6. So it tends to infinity, right? So the area of the surface of Schwarz lantern may tend to infinity. You see, you make slices thinner and thinner, right? But triangles are smaller and smaller. But it is constructed in such a way that the total area tends to infinity. So it means this definition, this attempt to define the area of surface as an inscribed, and you see, Schwarz lantern is inscribed, polyhedral surface, which is inscribed into our surface, right? But nevertheless, this, so you see, geometrically it seems very good definition, but not. Geometrical intuition doesn't work here, as this example of Schwarz lantern shows. So, okay, I spend a lot of time, of course, for this Schwarz lantern, but I like it very much. This story, which shows that it is sometimes it is very important to think about definition. And you see very famous mathematicians, I mean, one of top mathematicians of 19th century, they didn't think about the definition and used the definition for a while. Schwarz disproved, constructed this counterexample. So, then let us return to our topic. So, we want to understand what to do with area of surface. So the same figure phi as in previous section, we rotate about y-axis, right? Yeah. And we want to compute the area of surface of that solid of revolution. But now we need to understand how to define the area of surface. And you see that now geometric intuition may be wrong. That is more complicated than volume or area. So, what we can do? We can refer to frustum of a cone. So, if we take a slant line, right, and we rotate that slant line, then we obtain frustum of a cone, right? And once again, this area of such a frustum was considered in school, I guess, right? Did you consider it in school geometry? No. Bad. Okay. How this area of surface, let me start with area of surface of the frustum. Okay, let it be R, and that is capital R, and this height of frustum is h. So I'll refer to the area of surface is equal to area of surface of the cylinder, which you draw in the middle, right? No, not in the middle. Let me. Yeah, that is in the middle, I guess. Yeah. So, if you rotate instead of this slant line the middle, then you obtain the same area of surface. I refer to elementary geometry. At the moment, no other tools, because we have no definition of area of surface. We can keep dividing the surface into shapes that we want to solve. The question is that if there is a counterexample to the surface of area, maybe there is a counterexample to volume of solid. No. As I said, the rigorous theory of volumes and areas will be presented in next semester, so no problem. And with areas of surface also there will be more or less rigorous theory, which will be presented not in next semester, but in fourth semester. So it is even more complicated. But for a while, we refer to some facts from elementary geometry. So, and then what is area of surface for cylinder? Roughly speaking, you multiply this length to the length of the circumference, right? So 2 pi radius times 2 pi radius is the average times h. That is area of surface for the frustum. Now, we proceed in a similar way as we did for length. So, we split into, we consider again a partition. Equals to D, right? And then we consider one small interval, right? And we replace our solid of revolution, we replace it by frustum of a cone. Which cone? Of course, we draw polygonal line inscribed into our graph. And then we rotate it. Okay, it's better. I made bad choice, sorry. Better to do it somewhere here. Yeah, frustum, to have a frustum. So, we have frustum of a cone here, right? Frustum of a cone. And we replace surface of our solid of revolution, right? We replace our surface by the surface of this thin frustum. And then, once again, we collect all of those thin frustums together. So, what we'll obtain then? The sum of areas of surface for frustums inscribed into our solid of revolution is equal to, let me compute it. So what we have, pi times, look, what is little r and capital R here? Little r, capital R, what they are here? Values of our function, right? At which points? xj minus 1, xj. So, f xj minus 1 plus f of xj. Now, what is, oh, not h, I'm sorry, not times h, times L, length of this slant line, that is important. I'm wrong with elementary geometry, sorry. So, what is length of this slant segment? Let's compute it. How to compute? So, it's square root of what? By Pythagoras theorem. What is it? Square root of this height, and this height is precisely what? Delta xj, right? Difference between points of splitting, delta xj. So that is delta xj in our case. Delta xj squared. That one here. That is delta xj. Delta xj. And then what is difference between y's? Difference between y's is f of xj minus f of xj minus 1 squared. That is our area of surface of the frustum. Okay? So, once again, we refer to a fact from elementary geometry, area of surface of the frustum. For a while, put aside how it was obtained. It was obtained somehow. We accept it. And using this fact, we compute the sum of areas of revolution. Right? Now we want to find what is limit of those sums. So as lambda of p tends to 0. That is the question, right? I have 5 minutes. So let me denote it by SP. So the question is, what is the limit of SP. And why we are interested in it? Because we'll accept it as the area of the surface of solid of revolution. So I think I'll finish with definition. Maybe once again I'll avoid definition. But look at this expression. Look at this expression. So, by Lagrange mean value theorem, what we conclude? F of xj minus f of xj minus 1 equals to f prime at a point psi j times xj minus 1 or f prime at xj times delta xj. So if we substitute it, then SP equals to what? Pi times sum I, oh not I, j, sorry, j here. J from 1 up to n, f of xj minus 1 plus f of xj times what? Times what? Times what? So look, we substitute here f prime at psi j times delta xj. Then we can put delta xj as a common multiplier outside. So what remains? What remains is 1 plus f prime at psi j squared times delta xj. And you see that that is very similar to an integral sum. Which integral sum? S of, let's say g p psi is sum j from 1 up to n, j of psi j times delta xj, where j is the following function, that is 2 pi f of x times square root of 1 plus f prime of x squared. Look. So what we do? Roughly speaking, we replace both xj minus 1 and xj by xij. If we replace each of them by xij, then what we have here? We have 2 times f of xij, right? 2 times f of xij, and then square root of 1 plus f prime of xij. That is how it is obtained, right? So you see, we are interested, from geometric point of view, we are interested in the limit of such sums, right? And they are very similar to those integral sums. And I'll prove now in next lecture that in fact both limits of SP and of those integral sums, they coincide. And it will give us the formula for the area of the surface. So, unfortunately, I didn't finish. Okay, thank you.